A square matrix A is invertible if and only if A is a non-singular matrix. If A is non-singular matrix, then A inverse exists. But what is the formula of A inverse? So A inverse is given by 1 over determinant A into adjoint A. Look at the first column here, we have the other two elements as 0. So when you expand, the last two elements become 0. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, Vidhyaashram School of Excellence, Mysuru. In this session, we are going to learn about the inverse of a matrices. So, as we already learned that inverse of a matrix exists for only for square matrices. So, now here we are going to find the inverse of a matrix with the help of a formula. That is how to find out inverse of a matrix. Here is a theorem that says a square matrix A is invertible if and only if A is a non-singular matrix. In last session we have learnt about singular and non-singular matrices. That is, if the value of the determinant is 0, it is singular. If it is not equal to 0, it is non-singular. If a square matrix is non-singular, then only the inverse of a matrix exists, and it is given by the formula A inverse is equal to 1 over determinant A into adjoint A, and we already learned how to find out the adjoint of a given matrices. Let's take few problems to find the inverse of the matrices. So here is matrix given. It is 2, 4, minus 2, 3. First, let us find out the value of the determinant. How to find the value of the determinant of 2 cross 2 matrix? That is 2 into 3, 6, minus 2 into 4, which becomes minus 8. So this is becomes minus of minus 8 is plus 8. So 8 plus 6 is 14. Now here, clearly this is not equal to 0 here. So what we can write here, therefore, A is non-singular. So if A is non-singular matrix, then A inverse exists. But what is the formula of A inverse? So A inverse is given by 1 over determinant A into adjoint A. Now we need to find out adjoint A. I have already showed you a shortcut method to find adjoint A for 2 cross 2 matrices. That is, adjoint of matrix A is written, that is, you have to interchange the principal diagonal element. So 2, 3 can be written as 3 and 2, and the other diagonal element has to be written in the same way, but you have to change the sign. So here 4 we have, just write it as minus 4, and here we have minus 2, just change it as 2. So this is the shortcut method to find the adjoint of 2 cross 2 matrix. That is, interchange the principal diagonal elements and change the sign of other diagonal element. You can't interchange it, just change the sign of the given values here. So this is the adjoint of the given matrix here. Now using the formula, that is 1 over determinant A divided by adjoint A. So what is the value of determinant we got? That is 14. So I can write it as A inverse is equal to 1 divided by 14 into, what is adjoint A? 3 minus 4, 2 and 2. So we have written 3 minus 4, 2 and 2. So this is the inverse of 2 cross 2 matrix. The same formula is used for all square matrices. Next one, minus 1, minus 3, minus 5, 2. So first let us find out the determinant A. So determinant A is to find, to check whether it is singular or non-singular. If it is singular, no need to find the inverse. If it is non-singular, use the formula and find the A inverse. So here we have determinant A. Minus 1 into 2 becomes minus 2, minus 3 into minus 5 becomes 15, plus 15. So this is minus 15, so minus 17. This is not equal to 0, hence it is a non-singular matrix. So now here let us find out the adjoint A of this matrix. So adjoint A, here we can find it as, so interchange these two. So we have 2 and minus 1. Change the sign of these two. Here it is plus 3 and here it is plus 5. So therefore, A inverse is 1 over determinant A into adjoint A. So 1 over determinant A means it is 1 over minus 17. We can write it as minus 1 by 17. And into adjoint A, that is 2, 3, 5, minus 1. So this is the inverse of the given 2 cross 2 matrix. Next one, 1, 2, 3, 0, 2, 4, 0, 0, 5. So here, first let us find out the value of the determinant. Since this is a 3 cross 3 matrix, we have to find with the row expansion or a column expansion. Look at the first column here, we have the other 2 elements as 0. So when you expand, the last 2 elements become 0. Now we can expand it. So 1 into, so remaining element, delete the row, delete the column. So 2 5s are 10 minus 4 zeros are 0. Next is minus 0 into anything 0 plus 0. So clearly we got the value of the determinant A is equal to 10 and this is not equal to 0. So this is how we are going to find the value of the determinant and clearly it's a non-singular matrix. Next we are going to find out the adjoint of this matrix. To find the adjoint of this matrix, we need to first find out all the cofactors. So let us find all the cofactors, that is A11, A12, A13. So how cofactors are found? By taking the minus of each element. So the sign will be in the form of plus, minus, plus. Next is first find out A11. So for A11, it is the first row, first column element. So the cofactor will become 10 minus 0. Hence it is 10. Next is for 2. Delete the row, delete the column. 0 5 is a 0, 0 4 is a 0. So we get 0 minus 0. Hence the answer is 0. Next is for 3. So delete the column, delete the row. 0 minus 0 again. So the answer here is, or the cofactor here is 0. Now first row elements is done. Now let us find the cofactors of second row element. So that is A21, A22 and A23. So here we come minus, plus, minus. So for 0, delete the column, delete the row. 2 5s are 10 minus 0. So it is 10 minus 0 which becomes minus 10. Next is A22. So delete the column, delete the row. 1 5s are 5 minus 3 zeros are 0. So it is 5 minus 0 which becomes plus 5. Next is for A23. Delete the row, delete the column. 0 minus 0 it becomes. So the value here is 0. Next, the third row elements, that is A31, A32, A33. So here we have plus, minus, plus. So for 0, delete the column, delete the row. 2 4s are 8 minus 3 2s are 6. So 8 minus 6, it is 2. Next is for 0, delete the column, delete the row. 4 minus 0. So it becomes 4 minus 0 which becomes minus 4. Next we have A33 for 5. So delete the row, delete the column. So 2 minus 0 which becomes 2. So now we have all the cofactor elements. So to write this in a cofactor matrix, you can write A11, A12, A13 or else directly you can find the adjoint A value. So if you write in this order, the matrix becomes then adjoint of A. So that is, instead of writing A11, A12, A13 in row wise, just write it in a column wise. Directly you will get an adjoint A. So now adjoint A is 10, 0, 0. So first column is 10, 0, 0. Second column is minus 10, 5 and 0 here. And the third column is 2, minus 4 and 2. So this is adjoint A. Now after this, for this, let us write A inverse. A inverse is equal to 1 divided by determinant A into adjoint A. So determinant A, we got the value as 10 and adjoint A is 10, 0, 0, minus 10, 5, 0, 2, minus 4, 2. So this is the inverse of the given matrix here. So you can divide each value by 10 also. So then you will get the matrix as, if you divide each value by 10, here it is 1 0 0 minus 1, and here it is 1 by 2, and here it is 0, and here it is 1 by 5, so minus 2 by 5, and here it is 1 by 5. So this is the matrix you will get when you divide it by 10. Now the next problem is here 2 1 3 4 minus 1 0 minus 7 2 1. So we have here determinant A is equal to 2 into, so delete the column, delete the row, minus 1 minus 0. Next we have minus 1, so we have for minus 1 4 minus 0. Next we have plus 3 8 minus 7. So here we have minus 2 minus 4 plus 3. So which is equal to minus 3, not equal to 0. Hence it is a non-singular matrix. So therefore A inverse exists. Now let us find the cofactors A11, A12, A13. So for this the signs are plus, minus, plus. And the minors will be the values which is inside the bracket. So for the first 3 it is minus 1 minus 0, and here it is 4 minus 0, and here it is 8 minus 7. So here we have minus 1, minus 4, 1. Let's find out the second row, minus A21, A22, A23. So here the sign is minus, plus, minus. Let's write the minus now. So for 4, delete the row, delete the column, 1 minus 6, which becomes minus 5 into minus, plus 5. Next for minus 1, delete the column, delete the row, 2 minus, so minus 7 into 3, 7 3s are 21, so it becomes plus 21, which is 23. Next is for 0, delete the column, delete the row, 2 2s are 4, plus 7. So 4 plus 7, which becomes 11. Next we will find out the last 3 cofactors, A31, A32, A33. And the sign will be plus, minus, plus. So for minus 7, 0 plus 3. So here it is 0 plus 3. So the value is 3. Next for 2 it is, delete the row, delete the column, 0 minus 12. So which becomes plus 12. Next we have for 1, delete the column, delete the row, minus 2, minus 4. Minus 2, minus 4, which becomes minus 6. So when you write this in a matrix in this order only, that is column by, then it becomes an adjoint A. Now we have A inverse is equal to 1 over determinant A into adjoint A. So therefore the value of the determinant is minus 3. So minus 1 by 3. If you write the cofactors in this order only, then it is adjoint A. Minus 1, minus 4, 1. And here we have 5, 23, 11. And there we have 3, 12, minus 6. So this is the inverse of the given matrix. If you want this, you can divide the entire elements inside the matrix by 3 and write one more matrix. So next question. Let A is equal to 3, 7, 2, 5, B is equal to 6, 8, 7, 9. Verify AB whole inverse is equal to B inverse, A inverse. So we have to verify this statement. First let us find out AB, then let us find out its inverse. Then we'll take B inverse and A inverse and its product. So let's find out AB. AB is the product of these two matrices. So now 3 6 are 18, 7 7s are 49. First row, first column. Next is first row, second column. 3 8s are 24, 9 7s are 63. Next second row, first column. 2 6 are 12, 5 7s are 35. 2 8s are 16, 5 9s are 45. So therefore here AB becomes 67 and here it is 87 So here it is 47 and here it is 61. Now we need to find out AB whole inverse. To find AB whole inverse, let's find out determinant of AB. So determinant of AB is 67 into 61. 67 into 61 minus 47 into 87. Now when you solve this, you will get the answer as minus 2, which is not equal to 0. Next we need to find out adjoint of AB. So adjoint of AB, since this is a 2 cross 2 matrix, interchange principal diagonal element 61, 67, change the sign of these two, minus 87, minus 47. So now let's see AB whole inverse. So AB whole inverse is equal to 1 over determinant AB into adjoint of AB. So here we have minus 1 by 2, 61 minus 87 minus 47, 67. So this is AB whole inverse. Now let's find out A inverse. A inverse is 1 over determinant A adjoint A. So here we have A. So let's find out the value of determinant A. So determinant A is 3 5s are 15, 7 2s are 14. So the value will become clearly, I'll write here, determinant A is 15 minus 14, which is equal to 1, again not equal to 0. Determinant value of B. So here we get 54 minus 56, which is equal to minus 2, not equal to 0. So this is determinant B. Now let's write adjoint A. We have 3 7 2 5. So here the value is 1 over 1. So the matrix A is 3 7 2 5. So to find its adjoint, interchange 3 and 5, change the sign of 7 and 2. So then it becomes 5 minus 7 and here it is minus 2 and here it is 3. So this is A inverse. Now B inverse is 1 over determinant B into adjoint B. So 1 over minus 2 will get. What about adjoint B? We have adjoint B, B as 6, 8, 7, 9. So it becomes here 9 and 6 minus 8 minus 7. So now let's see B inverse into A inverse. B inverse is minus 1 by 2 and here determinant A is 1 only into, here we have 9 minus 8 minus 7, 6. And here it is 1 only. So 1 into anything is the same. 5 minus 7 minus 2, 3. Let's multiply this. So we have minus half outside and this is B inverse into A inverse. So we have 9 5s are 45 plus 8 2s are 16. 9 7s are so 63 and here 24. Next 7 5s are 35 minus 6 2s are 12. Next we have 49 plus 18. So the answer is here 61 minus 87 minus 47 and 67. Outside we have here 1 by 2, that is minus 1 by 2. Hence clearly you can see here, if you consider this as equation 1 and consider this as equation 2, both are one and the same. That is both are minus half into 61 minus 87 minus 47, 67. So therefore what I can conclude, that is AB whole inverse can be written as B inverse into A inverse. Hence we proved. Next one. If A is equal to 3, 1, minus 1, 2, show that A square minus 5A plus 7I is equal to 0. Hence find A inverse. First we need to find out this equation is 0. That is, we'll get a null matrix and then we have to find out A inverse. So this question they may ask you for 4 marks under the part A section. So that is the last part. So a very important question here. First let us solve this equation. Let's find A square. A square is 3, 1, minus 1, 2. 3, 1, minus 1, 2. So we have here a square is equal to 3 3s are 9. 1 into minus 1, minus 1. Next is 3 1s are 3. 1 2s are 2. Minus 1 into 3, minus 3. 2 into minus 1, minus 2. 1 into minus 1, minus 1. 2 2s are 4. So this is a square. So we have 8, 5, minus 5, and here we have 3. So let's see now. A square minus 5a plus 7i. So here a square is 8, 5, minus 5, 3. Minus 5 into a means 5 into a, that is 3, 1, minus 1, 2. So let's multiply 5 now. 5 3s are 15. 5 1s are 5. Minus 5, next 10. Next we have plus 7i. So 7 into I means 7 into 1001 matrix. So we get 7, 0, 0, 7. Let's see this now. So we have 8 minus 15. Minus 15 plus 7. So which becomes minus 7 plus 7. So the first one is 0. 5 minus 5, 0. 0 plus 0, 0. Minus 5, minus of minus 5 plus 5. So minus 5 plus 5 get cancelled, plus 0, 0. 3 minus 10 minus 7. Minus 7 plus 7, 0. So clearly we got the equation as O. So therefore, a square minus 5a plus 7i is equal to null matrix. So now we have shown that the equation a square minus 5a plus 7i is equal to null matrix. So we will pre-multiply A inverse on both sides. So let's split this as A inverse into, here it becomes A into A, minus 5 pre-multiply. So A inverse into A plus 7 into A inverse into I, A inverse into O. So here A inverse A is I. We already know that when you multiply the inverse of a matrix with itself, that is when we say that A is the inverse of B only when A into B, B into A is equal to I. In the similar way, A inverse into A or A into A inverse is equal to I. So I into A minus 5 into I, and here we have A inverse into the identity matrix is itself, A inverse, and here it is O only, because when you multiply null matrix with any other matrix, the answer is null matrix itself. Next we have A into I. So what is A into I? It is A only. And here we have 5i plus 7A inverse is equal to 0, or 7A inverse is equal to 5i minus A. So let's solve this. 7A inverse is equal to 5i means it is 5, 0, 0, 5. Minus A means 3, 1, minus 1, 2. Let's solve this. 5 minus 3, 2. 0 minus 1 is minus 1. 0 minus of minus 1 is plus 1. 5 minus 2 is 3. Now we need only A inverse. So therefore it is 1 divided by 7. 2 minus 1, 1, 3. So this is the inverse of the given matrix. So this is a 4 marks very important question from the determinants. That is, we have to show that the given equation is 0, and hence by pre-multiplying A inverse on both sides, we can find the inverse of the given matrix. Next question. If A is an invertible matrix of order 2, then determinant of A inverse is equal to. So we have options: determinant A, 1 over determinant A, 0 or 1. We know that A into A inverse is equal to 1. And also we know that determinant of A into B can be written as a product of determinant A into determinant B. If you apply determinant on both sides, so determinant here, this is I. Determinant A into A inverse is equal to determinant of unit matrix. So this can be written as determinant A, determinant of A inverse. Determinant of unit matrix is always 1. Now this is determinant of A inverse is 1 over determinant A. So which is one and the same? That is determinant of A inverse is nothing but the same, no? So which is 1 over determinant A. Hence option B is the correct answer. So this is how we are going to find out the inverse of a matrix with the help of a formula, and one of the important questions have been already discussed here. So in the next session, we'll see the application of matrices and determinants. Until then, keep watching, keep learning, keep exploring. Thank you.